Okay, welcome back to Apollonius, and today we'll be doing proposition 16. 16 is another conjugate diameter proposition, much like 15, but where 15 was talking about an ellipse, proposition 16 deals with a hyperbola. So as a reminder, a conjugate diameter is when you have two diameters and lines drawn parallel to one diameter are ordinate-wise to the other diameter and vice versa. So in this case, we've started with diameter AB, and we've drawn a line XD through C, where C bisects AB, and XD is drawn ordinate-wise. And we want to prove that XD is the conjugate diameter to AB, so what we need to do to prove that is to drop a line GH, which is parallel to AB, and prove that GH is drawn ordinate-wise to XD. And to be drawn ordinate-wise, it needs to be bisected at the point X, so that GX is equal to XH. So basically, if we prove that GX is equal to XH, then we'll prove that XD is a conjugate diameter to AB. So our first equality is going to be GK equals HL. So that'll be GK and HL. And I've drawn these sort of so that they don't look parallel, but they're both drawn ordinate-wise. And they're both opposite sides of the parallelogram, GH, LK. So GK equals HL. And then we square both sides, and those are also equal. Then we have the square on GK is equal to the rectangle AKKM. So that's just the square on an ordinate here is equal to the figure AKKM, which is this. And that's from 112, that's just a property of hyperbolas. As we've constructed the kickstand AE. And then on the other side we'll do the same thing. We have the square on the ordinate over here, which is HL, is equal to the area LBFN, and that's the same logic. So then if we have the square on GK is equal to the square on HL, and we substitute. Sorry, that was very loud thunder. If we have the square on GK is equal to the square on HL, and GK is equal to this rectangle, and HL is equal to this rectangle, then we substitute, and these two rectangles are also equal. That's our step 1. So in step 2, we're going to start out with AE equals BF. AE is here, and BF is here, and they're both our kickstands or upright sides, whatever you want to call them. And from 114 we proved that in a hyperbola the kickstands on either side of the section are equal, so these are equal. Then we have as AE is to BA, BF is to BA. Now I wrote down similar triangles here, but actually it's just AE and BF are equal. AB is the same line, so equal has a relationship to the same thing as equal has a relationship to that same thing. And then we'll look at these triangles KMB and AEB. So this triangle inside of this triangle, and we'll have as AE is to BA, KM is to LK. Or sorry, KB. Yeah, KB. And then we'll do the same thing with these triangles, ANL and ABF, one inside the other. So as BF, this line is to BA, this line NL is to LA. And I said it right that time. Okay, so we have our similar triangles set out. So we have AEBA, and we'll substitute that for MKKB on one side. So we bring that down here. And then on the other side we have BFBA, and we'll substitute that for NLLA, and bring that down here. So that's our substitution step. Let's take this side of the proportion, rewrite it, and then multiply each side by the common length Ka. And when we do that, it'll retain the same ratio because it's multiplying by the same thing on both sides. So we'll do that on one side, and then on the other side we'll bring down NLLA, and we do the same thing, but we multiply by LB. Multiply NL by LB, multiply LA by LB. And since you're multiplying the same thing on both sides, it retains the same ratio, same idea. So then we have MKKB, and we'll substitute that for this on this side, and then we have NLLA, and we'll substitute that for this. And that's how we get this whole thing. And I won't read that out, but it's just what I've just circled. Rewritten. And then we have an alternando step. That just means we bring down the things on the ends. These are the exact same. And then we switch the two terms in the middle. And you can look at Euclid 516, but it's a step in ratio manipulation called alternando, and it's just this process. Okay, now part 3. We're going to bring down this earlier result. That's why I ended it there. And I'll just rewrite it as MKKA is equal to NLLB. It's the same thing, I've just rearranged the lines because it's how it's written in the book. And MKKA, you'll notice, is here, and NLLB is here. So usually we say as this is to this, this is to this. As this is to this is equal. So this side, rectangle KBKA, must be equal to rectangle LALB. So that's what I've written here. They have the ratio of equality. Now we'll take these rectangles and we'll do reverse means and extremes. I just went over this in the last video, and I'm tempted to not repeat it. So all we have to do is look at one rectangle and see, are these two lines KB and KA either on the means or on the extremes? In this case they're on the extremes, KB and KA. And in this rectangle we have LB and LA on the means. So that's proper reverse means and extremes, and it checks out. Then we're going to do a step called componendo. This is also in the previous proposition, so I'm not going to go over it, but you can always look at Euclid. But basically it's just, if you have an antecedent and a consequent, and then on one side you add them together, and then you have the same consequent, and you do that on both sides. So you added LAKA also. Then it retains the same ratio. So instead of BK we have BK plus LB is to LB, and instead of LA we have LA plus KA is to KA. So I'm going to check that, move on, And then instead of writing BK plus LB and LA plus KA, we're going to look at the diagram quickly. We've got BK and we've got LB. So another way of writing that would just be LK. So we wrote LK. And same thing here, instead of LA and KA, KA, LA. So another way of writing that would be LK, or KA, KL. So we replaced both of these with the term LK. So if something has the same ratio to equal things, then they will be equal. So that means LB is equal to KA. And AC is equal to CB because we constructed the point C so that it would bisect the diameter AB. So of course AC is equal to CB. So we're going to look at LB and KA, which we've just proven equal, and ACCB, which we've also just proven equal. So that must mean that KC must be equal to CL, because we're adding equals to equal things. So now we'll look at this diagram, and we have KC is equal to CL within these parallelograms GKCX and XCLH. And since they're parallelograms, then we know that KC will be equal to GX and CL will be equal to XH. So that means that GX must also be equal to XH. And that's what we were trying to prove, because we were trying to prove that the supposed diameter XD is a conjugate diameter, meaning that it would bisect lines drawn parallel to our original diameter AB. And GH was drawn parallel to AB. So that's our QED.